Right. Welcome to JFool. This is my first time at JFool, so thank you for the selectors for letting me come. I'm Steve Poole, obviously, that's me. I did a talk like this in Geekon. I don't know if you've gone to the Polish Geekon thing, really great thing, and I'd never been to talk to a cinema before, and I turned up, and they gave me this massive room and a screen which is much bigger than that. So I thought, I can't miss the opportunity. So I put up a picture of my whole face on the whole thing and took a photograph of it, because then I had a 50-foot face, and I went, that's really cool, right? So I haven't done that this time, right? But anyway, so I work for IBM, I'm a developer advocate, but that's sort of the fun bit of the fact that I work for the Java team and I do runtimes, right? And I work in the UK, right, blah, blah, blah. This talk is about the far future, which is more than next week, right, more than next year, right? Some of it is here already, some of it is still coming. The point about this talk is to explain to you where Java's going, what we think Java needs to do, and to get you starting to realize how scary the future is going to be for you and your skills and how you've got to think differently. And we're going to talk about, indeed, not particularly much in detail, but just the principles of cloud, which we're all getting to deal with, data analytics, and machine learning, and then more stuff, right? And I hope I'm going to show you that whatever anybody else thinks about programming languages, we, i.e. the company I work for, and other companies, believe that the best way to get where we want to go is off the back of Java, right? So 1992, 25 years ago, I joined IBM. I came for 3 years, and I just stayed because it was fun, right? And I got hired because they had this thing. I had all these skills in this thing called AS400. Anybody heard of iSeries, AS400? Oh, that's really good. I asked that in other conferences, and it's like, Right. So, platform. I got hired because I had platform skills, deep platform skills, right? That's when we used to do that. But nowadays, and for the last 20-odd years, we've picked this thing. Java, within a couple of years of us getting involved, became the platform, right? I spent a lot of time working with the Sun guys, the Oracle guys over the years, and it's always been a pleasure. And the thing has always been, we have Java, it runs everywhere, it's been brilliant. You know, well, however you look at it, it sits on every OS you can think of. It does memory from tiny devices to big devices, you name it, toasters to mainframes. Java's everywhere. Yeah, everything. Well, not quite so much. Over the last few years, Java's not been everywhere. It's struggled. Part of the reason is because of the way that we evolve the language. So we did some really cool stuff, didn't we? You've seen modules have just arrived in Java 9. Really good. Took 10 years. Partly because it's really hard, and partly because of the way that these things are delivered. And it's the same with Lambdas. Took 5 years. Hard thing to do, but hard to deliver. And other programming languages do things differently. Much more incremental delivery. Little things, try it out, take it away, try it again. Okay? With Java, we haven't done that. With Java, we've done big bang evolution. Badunk, here's something. And that's not really cutting it anymore. And we need to think about how we change that. Because modern things like cloud and data analytics and machine learning have new requirements on Java. So we have to find ways of getting back there. So the question really is, we had a lovely dominance, and if anybody here, I'm sure you're going to say, yeah, I program in Node or Ruby or Python, or you name it. Somebody goes, yeah, I use that for something else, right? So we need Java to get back to being that platform, and I will show why that's a really good thing to do, right? And so we have to figure out what the challenges are, and we have to deal with it. One is definitely how quickly we can get code out, and I'll talk about that later. But the other thing is also, well, what are the important bits about these programming languages that make us think, why can't I do that in Java? Right? So we've got to make sure that Java can deal with the challenges that these languages have. That for very good reasons, these things are out there being used. We want to get some of those characteristics back into the Java space, right? So let's have some fun, right? Let's have some races. So I'm going to go through 4 benchmarks. So here's the first one. So one CPU, n-body. What does it do? It's a benchmark for calculating the positions of Jovian bodies. So it does number crunching, and it says how far, I think it's all the Jovians, and it's like 500,000 incremental positions. So it's predicting where the planets are going to be, right? Of course, the answer is, and the language that gets there the fastest is the winner, right? So I line them up. Here we are. Okay, here they go. Okay, who thinks Ruby is going to be the winner? Who thinks Ruby can do maths better than anything else? Okay. Anybody want to have a go? What about Java? Java programmers. Is Java going to win? Oh, okay. Well, let's see what happens. This is basically real time. These are seconds. Okay, so there we go. The neck and neck through the 5-second mark. Here we go. 10 seconds. Oh, okay. They're still going. Here we go. Nobody finishing yet? 15. Oh, it's going to be boring, isn't it? It's going to be ahead. Come on. Somebody's going to finish in a minute. Ah, Java finished. Go finished. Swift finished. Excellent. Okay. Yeah, oh, no, look at that. Excellent. Do you think Ruby and Python finished? Here are the numbers. Oh, okay. I hope there's no Ruby or Python fans. Actually, I'm a Ruby fan. Yeah, but, yeah. Anyway, so let's do something else. Let's look at that. So CPU time, it's always the basic stuff. There are the CPU time for each of the languages, how much memory it uses. So you can start to draw some conclusions. Well, CPU time isn't much in it. I took off Python and Ruby because the charts would then be so tiny. Then you look at the memory stuff, and what have you got? You've got Java uses lots of memory, so does Node. Go uses hardly any in this thing, and Swift is also fairly reduced. Cool, okay. How about another one? Mandelbrot. So this is, the old Mandelbrot set. We've all seen it. It's calculating one. So you basically create a big grid, and you're going to go through and do the calculations on every element, and then you're going to save it to an image file. Okay. This thing uses multiple processors, so it'll be interesting to see what happens. Right? Okay. Any volunteers? Who thinks Ruby and Python might finish? Okay. Yeah, it might finish. Yeah. So let's see what happens. Here we go. Right. Oh, wow. Look at that. Swift, Go's finished. Java's finished. Okay. Let's wait for them. Here we go. Are they going to finish? Hey, Node finishes. Yeah, we know what they do. Yeah. Right. What happens? Here we go. Wow. Swift, 3 seconds. Java, 6 seconds. They're not too bad. And then Python and Ruby, well, they're still measured in minutes, but they're slightly better than the time before. Right? Node, 20 seconds. So again, if I put a look at the thing, CPU time, it's all much of a muchness. Memory size, you can see in this pattern, Swift, Go, really good at memory management. Node, not so much. Okay? But there's another take on this as well that you need to think about, because these are benchmarks, these are all running on a four-core thing, right? So the very first one we did, we just used one core, unless we're using all 4, and you can see basically the usage. And in this particular benchmark, pretty much all the programming languages, apart from Node, were good at managing to use all the CPUs. That's an important consideration, right? So we've looked at single CPU, multiple CPU, how good at number crunching. Maybe there's some trends coming out. There are other things that we care about, things like garbage collection. So here's another benchmark that is basically you create this binary tree and you mutate it. And you mutate it rapidly according to the rules of the benchmark. The fastest does it, right? So partly it's a matter of measuring how quick a garbage collector works. Okay. So which of these have good garbage collectors? Do we think Swift, Java? Okay, so who thinks Java's got the best garbage collector ever? Okay, excellent. Who thinks Swift has got a good garbage collector? Okay, well, okay, yeah. Who thinks Ruby's got a good... No, let's just not go there. Right, let's run the benchmark. Who's going to finish first? So, Java or Swift. Oh, and Java. And there we go. Oh, okay. Wow, which one's going to be? Is it going to be, yeah, which one's going to, well, there we go. Yeah, and yeah. Okay, did they stop? Well, they did, but not here. They in the next room, okay? Right, so, wow. So, Swift, 5 seconds. Java, 9. Go, 35. Mind you, Go is a compiled language. You'd think that would be quite good at this sort of stuff. Node, wow. But Ruby and Python comparatively are quite good coming in, right? So you can see in this particular benchmark, again, that Java takes a load of memory and so does Node. And then when you look at the CPU usage, you get to see some interesting patterns like Node, right? Not really good. Swift is pretty good, but not brilliant. Java's not bad. These ones, well, Go, yeah, maybe. And I'll come back to why you can't always take this as valid, but it's a good trend. So let me show you one last race. So regular expressions. Basically, it's a benchmark where you're going to try out the regular expression parser for your programming language. Right? There's a whole bunch of rules, but actually it just comes down to who goes fastest. So who thinks that maybe something like Ruby or Python has a really good regex support? Okay. When I say good, I mean fast. They're not necessarily the same. What about Go? Okay. So Node, Node got good? Yeah, Node's not very good at this, is it? Swift. Oh, okay. What about Java? Has Java got... You guys aren't playing, are you? Okay. So what happens? Let's run this one. Okay, here we go. And who's going to finish first? Wow. Well, what happened there then? Node finished, and then Java's finished. And wow. That's interesting. So they just keep going. Well, Python finished. And, yeah. So, that finished. So, what do we get? Node, which has been pretty slow, 4 seconds, right? Java, 10 seconds, blah, blah, blah. You can see Swift, 75 seconds. Okay, what's going on here? We'll get some more data. The CPU time, yeah, we don't really care because there's not much in it. Memory, a lot of memory usage. Swift, which was slow, didn't use much memory, so that might be why it was slow in this case. Node, comparatively to all other things, has come down in memory, right? And it was really fast. And Java's sort of where Java usually is, right? And I don't mean that's not a bad thing, right? There are reasons, and I'll talk about why that's the case in a second. Right? And if you look at the CPU usage, Java, one of the strongest things we can say about Java in this space is Java is very, very good, because we've spent many years working on making Java fantastic for multi-threaded environments, right? Whereas things like Node just sidestep the issue. It's not a challenge for them they wanted to take. But then you can see things like Swift and Go, they're really struggling to make use of this. Now, Node only used one thing, but it's still got fantastic support, right? And the reason is that it has a really good native library support. Right? So part of this is when you're picking a language, you have to be careful about how you approach it. So there's this old myth, it's been around forever, about some blind people who are introduced to an elephant for the first time ever. Okay, and depending on which side of the elephant you get, the side or the trunk, you figure out, excuse me a second, otherwise that's going to be going off all day. So you figure out, depending on the, no, that's not going to do it either. I don't actually know why that went off. Right, so depending how you come at something, you get a different impression, right? And that's the same with benchmarks, right? And all the benchmarks I've shown you come from, or the elephant, come from this place, benchmarkgame.blah, aloth.debian.org. The intention is not for you to use this to compare programming languages. It is a very good way to understand how to write code because they're little tiny 100-line benchmarks, right? And people try this and submit new ones and we get better performance. Okay, in all these programming languages, you can go off and get these benchmarks. Okay? In all these themes so far, we would say Node's not been very good in this space, right? Java's not been as good as we thought. Swift has been quite good. And some other programming languages like Python and Ruby are tremendously worse than maybe we expected, right? So you have to take that with a pinch of salt, of course, because it's benchmarks, right? But there are trends. But before I just talk about that, I just want to play fair with Node, right? Because I could diss it, and we could say, oh, it's really slow, but it's good at reg expressions. Well, so this is a screenshot from a application metrics tool, the open source tool that IBM produces from the runtimes team. The thing I want you to take around is on the top, right? So this is a benchmark. It's not really a benchmark. It's just a load. We have a system. We're just loading up 3 different processes. One's Node, one's Swift, one's Java. The thing to bear in mind is to look, if you can, at the top line and look at the scales. So basically this is asking Node and Java and Swift to give the quickest response to an HTTP request. So, zero data, just like how quickly can you say respond. The Node side, you can see that it's measured in 8 milliseconds as the spike, but actually if you look at the line, it's right in the bottom. Swift, okay, same sort of scale, but further up, and Java's on a much bigger scale, right? That's why people use Node, because of that characteristic, right? So anyway, don't take micro benchmarks seriously, but they are interesting to give you trends, right? So we've said Node is really good in the I/O space, really good for non-blocking stuff, but don't do compute-intensive things. It's not very good at it anyway because of the way the programming language is designed, but also because of the single-threadedness. Unless you move to multi-process environments, it's just slow, right? So it's not something you want to do, but that's fine. You use it for what it's good at. And if you look at the other languages, you can see things like Go looks really good, but Go is designed more to do with C space than it is with the Java space. Maybe we'll get Go turning up in the JVM at some point, right? And then you've got things like Python. So why are people using Python for data scientists machine learning? I don't know. Well, actually, the main reason is because there's a whole bunch of native libraries. Python's really good at that. So the most amazing thing is you'll find lots of the machine learning and data science libraries that are being used by Python are actually written in Fortran, right? But Python is the glue, really good native memory and native library connectivity, right? So we, having looked at all that, IBM's going, well, where do you put your money? What's important? So we've picked 3. Node, Java, and Swift, because between them, they cover all of the bases in terms of technologies for modern cloud applications, whether it's Node at the front end and Java at the back, Java doing the heavy lifting, Node doing the data transfer, Swift if you're trying to put things on small devices like iOS, so great. That's where we're going. It's really good for cloud. And the thing about cloud is as far as this talk is concerned, we're sort of know what we're doing. And in terms of your impact, the impact on you as a cloud developer is you're going to see stuff coming, right? You're going to see container support. Well, in Docker support, it's getting better. You're going to see faster startup time because we know in a microservice environment, JVMs are going to start up even faster. We've got to have smaller footprints, right? So if you go and get the OpenJ9 binary, so you can go to adopt OpenJDK and get the OpenJ9 plus OpenJDK binary. Hello, yes? So the reason is that you have to do a lot of the heavy lifting. You have to write the code yourself, right? So it's more about how much investment. You could write some really good stuff in C, in Go, but it'd be the same as if you're writing it in C, effectively, right? The runtimes are much better. The other runtimes are much better at giving you a platform, right? Anyway, so what was I saying? Yeah, so there's a bunch of stuff coming. And you can go see this now. You can go and get our OpenJ9 binary, and the thing you'll get out of that, out of the gate, will be improved memory footprint. Right, you can go get that now. Right, so we've made memory footprint twice as good. So if you're running something in the cloud and you're paying money for memory, because that's what you normally do, if you use the OpenJ9 one, you get performance improvements, you get smaller memory footprint, it saves you money, right? And that's what we've got in our one, but it'll come up in hotspot, because we're all working. We know where we're going, right? The question is more about what's happening in these other spaces. What's happening in the Java space for these? So I need to talk about those three runtimes as an example of why we think Java is the right place to put some of this stuff. So let's pick those three things. So the first thing to remember, of course, is that actually, as I was just saying, is that actually they're all written in C, right? That's the ironic thing. As I joined the Java team, I found very quickly that I didn't write much Java, I just wrote C, right? So we have these things, right? And they have different characteristics, right? Runtime language. Java is a runtime language. It has a VM, right? It's a runtime. It's a platform. JavaScript is a scripting language. It goes from script to machine code, right? And Swift is a compiled language, right? So there's no jitting in that sense, right? But Java's type safe. One of the biggest values that the Java has over everything else, and for the future, is type safety, right? Because it means that not only can we get better performance, because an int's an int all the way through, and then we can optimize, right? With JavaScript, for instance, you don't know whether an int's an int until the very last moment that you use it. And that's a problem when you're trying to build high-performance runtimes because you can't optimize enough. But with JITs and type safety, you can optimize and re-optimize and re-optimize, right? Whereas if you have static compilation, you have done it once, right? And if your workload changes, then you can't do that. And I mentioned JIT as a service because that's something that's coming where we'll start to be able to measure what you're doing in a Docker container, for instance, which is going to be short-lived. We're going to profile you, save the profile, and maybe the JIT code, and next time be able to catch up from where you were so we don't lose the data, right? And then you have, bytecode, right? As I said, JITs are really good at this, right? We've put so much effort into it. And the wider the picture that we can see, the larger piece of the program we can understand, the better we can do that. And we have a garbage collector that is second to none. There's no doubt about it. We have worked hard to make garbage collection work in a multi-threaded environment, right? We tackled all the big problems, right? Yes, it means you use more memory, which is why many of our benchmarks have more memory. And we're all used to tuning a JVM to work out memory through, how much memory I'd use to get the throughput before it runs out of memory and all that sorts of stuff. And that's driven by your garbage collector, right? So our garbage collector, right, the Java garbage collector is by far the best, right? Swift, for instance, uses reference counting. So that just says every time I pass an object around, a little number and it goes up, and when I've sort of dereferenced it, the number goes down, and when it gets to 0, I try and delete the object. The consequence of that is that garbage collection takes place at the point where something gets to 0, and that could be anywhere in your code. When you've got a garbage collector running in the background, it's not hitting your throughput, it's balancing your throughput, right? Oh, and you don't get circular references, which is, with reference counting, it's circular references, which means you have basically circles of objects that all think that they're live, but actually nobody's using them. And Java doesn't do that. Java does the absolute maximum to ensure that all the data you've got, all the memory you've got, is being used effectively. Right. And the threading. Java's concurrent threaded. We have worked like anything over the years to deal with the consequences of synchronization, threading. It all goes together, right? The JIT gets in there. We have optimized the runtime in so many ways because we tackled the problems, right? You don't need to do that in JavaScript because it doesn't have that as a design principle. But then you have the problem that if you try to use anything that's CPU intensive, even if it's not number crunching, will slow your process down. Right? So when you look at this stuff, you can say these are the things that we care about. The platforms that they run on, we care about. Right? So, okay, these two run on these things. It's really hard to put JavaScript on a new platform because JavaScript goes from JavaScript to machine code. So if a new platform came out, a new architecture, somebody has to do the heavy lifting to move it across. When you've got a VM in the middle, it's much easier to do. Right? So from our point of view, all these things, from type safety and JITting, right, having a platform means we can take this thing forward in ways that we wouldn't be able to do other programming languages. Right? Nothing else comes close. It really doesn't, right? And when we start talking about what's happening in other parts of the ecosystem, so like Oracle donating J2EE to Eclipse, everybody's heard about that, right? That's a really good thing, right? We're open sourcing everything. That's really good because we need to work together to make this happen. But we need to get the cadence up. One of the things you'll heard if you listen to Mark Reinhold at Java 1, again, he was talking about we all need to get the cadence up, right? And so the biggest change that you're going to see, like now, is the fact that you're going to be getting these 6-month releases from Java, and some of those are going to have experimental things in, and then they're going to disappear, right? They're going to come, they're going to go, they're going to come, they're going to go, right? But that's really good, right? And everybody can get involved, and it's a call to arms really. If you're not involved in open source or Java, well, there's a great opportunity for you to do so, right? And there's loads of stuff, right? And getting this faster cadence together means we can start to tackle some of these other problems because we can get stuff out to you. You can try it, you can feedback, right? And you can try that on all sorts of open source implementations. Variety, whether it's J2EE or OpenJDK or whatever, variety means we can try different things. Each of these code bases has a different reason for existing, has a different design point. So which one goes forward with which set of technologies will depend on where they started, right? The thing is, and this is getting really to talking about what's really going to happen, is we have a runtime, we have a VM, we have an ecosystem that we're changing to make it faster. We have multiple implementations of the pieces. That's all really good because that gives us such a big wealth to pull on to get out to the next level. What's going to happen next, right? Right. And we're going to take you to places that you weren't expecting, that James Gosling never expected Java to go. Okay. So I can talk about cloud, but I would say in this talk, I'd say cloud we're pretty much sorted, right? We have lots of challenges, but we know what we want to do, right? This isn't the big stuff, right? The big stuff is when you start adding in machine learning and data analytics. One of the things that's big change is every piece of data can now be analyzed, right? And that's what's happening. So the question is, how do you get the analytics and the machine learning close to the data? how do we make JVMs more able to realize those requirements? So you can see tailoring responses to the personalities of your customers without meeting them. These are all real use cases that people are coming along. I want to do this, right? How do I do this? So as a developer, you're now going to change from writing code the old way to starting to do new things, right? And that's the biggest challenge for us, is we've got to solve problems differently. So I'm going to take you through a few examples and talk now about the future. So I'm going to use a use case, an example. Word search. There's the grid. There are the words. Here's the problem. Find which of those words is not in that word grid. Okay? Now, it's not an exercise. You don't have to do it, okay? Right. How would you do that? So you might say, well, I'm going to take my list of words and I'm going to go through every word in the list, okay? And I'm going to see if that word is in the grid, right? And I'll record it. And then at the end, I'll look at all the ones I found, take them away from the list, and I'll be left with the ones that I didn't find. Okay, cool. And that's straightforward. And you end up with things like that, because that's interesting. IBM, backwards, because word searches go left, right, up, down, backwards, 8 directions. So you have to deal with that. And the chances are, the first time you do this, you'll do something awful like this. Right? You'll do X, Y, find something, up, down, left, right, okay? And you can do that. And as those benchmarks show, when you do things, you can end up with total inefficiency. So if I just do a for loop, or a nested for loop, what do I get? 1 CPU. Didn't multi-thread it. Multi-threading. So luckily, we have lambdas. So you could think differently. So rather than thinking of a grid, you could think of it as a stream of locations. So you could create something that looks a little bit like this. You can have an int stream where you say, give me 0 to however many elements there are, which is the first line, and then you can do a parallel for each, put a lambda in there, and with a little bit of maths, you can take that number and turn it back to the xy coordinates. You do that, and now you've got a parallel activity. Now, how many of you are actively writing lambdas? Excellent, okay. So you're going through this thought process. What you have to do is start thinking about changing the data, right? It's not just about coding, right? So that example, when you run it, multi-threaded, however many CPUs you've got, you get some benefits. But you still have crappy code, right? You've still got this crappy code. And one of the reasons that you have this code, like while the length of the word and its offset and its dy and dx and all that stuff, you go, why am I doing that, right? Because if you have a moment to think about it, when you're searching for a word in a word grid, you have positions around the edge where you might have a starting letter, like you might have J at the top. So there's Java in the middle, right? But I might hit that one. So what do I do to make sure I don't drop off the sides of the grid? Okay? And so you write code that's like that, where you're checking your positions, right? It's not the only way to solve the problem. And in fact, going forward, it's exactly the wrong way to solve the problem. Right? Going forward says, think about changing the data. So one of the first things you can think of is, well, I'll put a big empty buffer around the outside of my word grid, all right? And so that and it'll be full of zeros. So there's no chance when I'm searching of running off the end. Right? And the buffer is as wide as the longest word. Okay? That sounds a straightforward way of thinking about it. Okay? And that's really good. So now you've got more space, and you can search. So your code gets a little bit, you can take out some of the lines. You're not doing the checking. You don't need to. And you can do different things. Again, you can think about the data. So you've got 8 directions. And rather than having 8 case statements or 8 ifs, you can think about it as a vector about the transformation. I'm going to take a point and I'm going to move it in 8 different directions. Okay, so let me encode the 8 different directions in an array, right? Rather than write if code, rather than if statements, right? And then I've got code that says, well, I can take the direction, right? So now I can say side. So how wide is the grid plus the buffer? Actually, times 2 probably, and then times 8 directions. So now I've got a number that goes from 0 to some very large number, whatever it is. And then I've got my lambda in parallel, and I take the number and I turn it back into the position, right? And because I've turned the direction into data, I don't have to have any if cases. I just go, well, whatever direction matrix vector I need, I'll just keep applying it. Right? And it's all straightforward, right? I'm not claiming that it's magic. What I'm saying is, from your point of view, the challenge is you've got to start thinking about changing the data, because the stuff that's coming up the pipe to us is going to require you to think like that rather than like lots of if statements, right? So the other reason, so 2 reasons. One is because of the hardware that's coming, but also because that's just an example of a tiny thing. Imagine when your word search is enormous, right? Billions of characters, because that's what you do if you're doing data analytics, right? What happens if you're searching for millions of words? What happens if the data's multidimensional, right? You're not going to write the code. You're going to change your process and you're going to think about changing the data, right? What happens if the word you're searching for is so long, supercalifragilisticexpialidocious, that the buffer's too expensive? Okay? Right. Well, then you get into things like this. Anybody here doing data analytics using Apache Spark or similar? I'm so disappointed. Okay, so think this. You've got a massive grid. You're going to do some word searches. There's your problem. And you have a bunch of nodes, and you want to get the data down to each node. And the first thing you go is, oh, that's easy. I'll just take that. I'll just break it into 4 or 5 or 10 blocks, and I'll send each block down. Easy. And then you realize, well, no, because I might have a word that goes across the boundary. So there are multiple ways of solving that problem, right? But But one of them might be, for instance, you might split the words that you're searching for into small segments, and you might then go give each of the nodes a piece of data and this tiny little grid that it will search, and it will tell you that it's got some potential matches, and then you do a second pass where you start joining those matches up to see if it matches words, right? It's not the only way of doing it, right? My point again is you can't take your thinking about how to write code that you run on a CPU, even if it's a multi-threaded one, and you can't shove it down to clusters. And when the data gets too big, you have to start thinking radically different. And actually, this works really well for things that are coming, because at the back of each of these executive nodes are CPUs. Cool. There's GPUs. Ooh. And there are a couple of others. FPGAs, programmable hardware. ASICs are hardware that are programmed for the specific problem. And they could be at the back end of any of these nodes that you're using. Right? So we've got, the OpenJ9 thing's got NVIDIA GPU support. Here's a problem for you. You've got all this data, and you want to get it down to a GPU. You want it to do some processing. Did you know that it takes time to transfer the data, right? And you may not get the benefit, right? Because the GPU may do a really good job, but it may take a lot longer to get the data there and back than you were expecting, okay? So you have to have a new thought process in your head when you're now designing your programs about the characteristics of the hardware that you're going to be executing on, right? Right? Because, for instance, like GPUs don't behave like CPUs. GPUs are SIMD, which I'll explain, right? So if you were writing standard code and you had some if condition, right? You'd say, right, run that on thread 1, run that on thread 2. They will both complete pretty much at the same, okay? The first one does step 1. If is true, say, does step 2. The other one, maybe the condition is false, and it does a second step 2. Okay? 1, 2, 1, 2. In parallel. That's what you'd expect. In GPUs, it doesn't work that way at all. GPUs have one program counter. So all of these thousands of threads, all these tiny, tiny little computers, all are in lockstep. Right? Dunk, 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 dunk. That means that if you go down a second path, all of your processors in this GPU, all the threads are going to go down that second path. For most of them, they won't actually do anything, but they all have to happen, right? Because at least one has done it. So it means if you're writing code to go down to a GPU and it has lots of if conditions and it's not data-driven, it takes the time it takes to cover all the paths you're going to execute on all threads, right? So now you're going to change the way you code this, right? This is coming, right? GPU support is in JVMs now experimentally. It's coming. GPUs are getting big. They're being used for data analytics. We're going to make it available in Java where everybody's working on what the model is going to be, but it's coming. And you will have to make that transition to use that, and you'll be thinking data. Right? A bit slow. Right. So what about, it gets even bigger. What about, for instance, you don't know what the words you're searching for? Suppose somebody gives you a word grid, and they said there's some words, and they go find it. Okay? So you could go, well, I'll go get a dictionary, and I'll put every single word in there, and I'll search for every single possible occurrence. Okay? However big the grid is, that's expensive. But it's not the way you'd actually solve the problem. The first thing you'd do is you give up a little bit on accuracy, and you might use something like a neural net. So, anybody using neural nets? Oh, a few, cool. So in Java, there's a whole bunch of deep learning for J and neural net. Really good stuff to get work going. What happens? You use neural nets to do searching after you've trained one to understand how words are constructed. Right? So you can do that. You can take a bunch of words and you can teach a neural network to work out sequence of letters. What should come after this one? What should come after this one? Then you take that and you apply it to your word grid, and it gives you a whole bunch of candidates, and then you go through the candidates and work out which ones are real. Okay? Much faster, but not perfectly accurate. If you're very lucky, you just get a bunch of false positives that you can chuck away. Maybe there's some words that weren't in the dictionary and they're a bit weird and they didn't get picked up, but that's tough. That's life, right? And the thing is, neural nets are coming not only to you in software, they're coming to you in hardware. These are lovely little architectures. They are mapped, you can see them, they are mapped on brains. They're on how neural network, how your neurons actually work. Right? They're event-driven, so they fire each other off, there's no sequence going on. They're almost here. And as soon as they're here, as soon as we get those into the back of the servers, then we start exposing it. I hope you're going to see that so much of what's happening and changing here, what's coming down the pipe, means we need to new data models. Right? And one of the things that we can do, because we have the VM, because we have your Java code and we have JITs, we can take your Java code and morph it to fit to these things. Now, you will have to do some of the work, but actually we can do much for you because we've got the JVM, right? We might get some new bytecode instructions. We might get some new operators, but those things can start to come down, right? And because we can, with the JIT can do the heavy lifting going from Java to machine code, we can do Java to GPUs, which we can do now, but I do Java to neural networks, right? The challenge is going to be that you have to think differently. No, I said that. Right, one more. So what's the most strangest thing you can think of? Well, how about this little algorithm? There was this guy, and he was called Mr. Grover, and he created this algorithm that said, if I have the right sort of computer, I can do word searches, or any search actually, in a fraction of the time it would take a normal computer to do it. The laws of physics says the time it takes to do a search is related to the number of elements in the search. And he went, well, actually, I can think of a way of doing it differently. The thing is, to do that, you need a cat and a qubit, right? Has anybody heard of quantum computing? Yes, quantum computing. This is a quantum computer picture. The quantum computer, this is really good. The quantum computer is a little tiny thing down here somewhere, right? The rest of it is to freeze the quantum computer so that the magic can take place down to 15 millikelvins, which I think is cold, right? This thing is massive, right? This is not round the corner, right? Well, it's sort of round the corner because you can go play with one now, right? We have reasons that they really exist. The challenge isn't that they don't exist. The challenge is making them big enough. So if you've ever seen pictures of old computers when computing started, they were massive things, wires and people and buttons and things. Well, we're sort of at that stage. These things weigh many, many tons. They're not coming to your laptop yet, unless you work here somewhere cold. But they exist, and you can use one now. Okay? That's an example of how you program it. You can ask, through the most amazing magic, you can ask a quantum computer to tell you whether a grid has a particular word in it. And you ask it, and it will give you a percentage back. And then you ask it again, and it will give you a better percentage. And you keep asking until you have faith. Right? If you ask too much, it may forget and tell you that it doesn't contain it. And then if you keep asking, it will come back. Right? Okay? And it's all to do with the magics of quantum computing. I would not want to give you any education because I keep going, I think I've got it. But you can go play with this now, and this is coming as well, because this is going to make a massive difference. We need lots of qubits. Currently, so qubits are, quantum inversion of a byte or a bit, and to do something serious like what the NSA want, which is to break large-scale encryption, we might need 1 billion of them. We're in the 10s, 20s at the moment. Okay? But once we get to the point where we can generate more of them, right, because that's the stage we're at, then suddenly the way that your search is working, the way that you write code, the way that you get the answer isn't going to be the way you were thinking. So you're going to start giving up accuracy for speed, and everything's going to be data-driven. It's all about changing the way that you view data and getting your head around these changes, right? So you have to present your data differently. You get statistical response with quantum computing, right? And that's the same sort of things you get with data analytics and machine learning. You're not getting solid answers, you're getting close answers, right? And the thing is, from a JVM point of view, we know how to do this, right? We know how to put new hardware under the JVM. All the things you're seeing, whether it's data analytics, machine learning, as we figure out what the best practices are, as we've done in the past, we can take that information and we can put it into the VM, right? And as I said, it may mean more bytecodes, it might mean new Java APIs, right? It may mean that you change things, but we can take that and we can put that into the VM because it's so much easier to do it there than it is to do it anywhere else, right? So we've got the cloud stuff. That's good. That's coming now. You've got microprofile. You've got all this great stuff that's happening that's now. Tomorrow it's all about data, right? Lovely marketing slide, but it sort of gives you by 2020, 1.7 megabytes of new information will be created every second for every human being on the planet, right? You have to start moving away from whatever data scale you work with now, unless you're really, really in the last top end, it's going to go up and up and up and up, right? You can't write programs the way you used to. You have to think about changing yourself, changing your attitudes, and dealing with data, right? We're all going to become data scientists one way or the other, right? And we're going to have to start learning machine learning because they're the tools that we're going to be using, right? And it's all coming here. It's all coming to Java because that, from a runtime's point of view, from an IBM point of view specifically, is where we think it should all happen, right? Right. So cognitive, data analytics, it's your challenge, but it's also our challenge, right? So however you're doing this, whether you're moving from old style code, I know, to neural networks, to big data, to quantum, right? You've got to think differently. You cannot code the way you used to, and you can expect the stuff to start percolating up. GPUs are becoming more and more ready, right? The neural net stuff, that's everywhere. The neural net hardware, further away, but it's coming. These are going to be your toolkits, and you think differently if you have to use them. And just to give you a plug, apparently, which I found out this morning, so I've just whacked this in, is my colleagues, who you can go talk to, apparently are running some quantum computing meetup. So if you're interested, I'm actually quite interested, you can go learn more. And of course, there's a whole bunch of stuff we're doing over outside, right? So that's it, really. I can give you a nice blue stripe with IBM on it. Or, in fact, I can give you the thank you talk, but that's it. I will tell you, you may be going, do I really have to do this? You really do. Your life is going to change, right? Microprofile and things like that, that's fine. But tomorrow and the day after, you need to be looking at data and you need to be changing the way you design things, ready for when that turns up. Thank you.